second one is that any quantum channel allows for the cross representation. So this is a cross representation, cross operators. And additional condition to be met is that the sum of the products in the context of measurements, these products give us the probability operators. So you have to meet the completeness condition, right? And yes, the particular case that we have started from is that when the cross operators are proportional to unitary, and we can talk about this statistical ensemble of unitary operators. And we have discussed this so-called Pauli channels, and they can be formulated as a randomly distributed unitary, right? So the next point, the next important point, is that cross operator, cross representation can be obtained from the unitary evolution. For example, we have things like this. We can enlarge our system. So this is our system. Think it as an auxiliary system or ancillary system or anything which is not our system. This is additional system. I would say this is the environment, and I can assume that the evolution of the combined system is unitary. It's described by unitary operators, evolution operators, right? So, again, after that, I can trace out environment. So I will have things like just use the index E to indicate that these are the states belonging to the helper state of the environment. So this is the orthonormal basis. And actually can see that this is identify these operators that was obtained after I performed the partial scalar product. So this is a partial scalar product. And after that, I will get the operator acting in the space of our system. So the other interpretation of the same formula is that you perform measurements in this environment in basis E, right? And this is nothing but the post-measurement state, and of course unconditional. So this is represents a case when we don't know the outcome, and it's not completely true because actually I have traced out environment. So I perform measurement, projective measurement, and trace out the system on which I have performed the measurement. So whatever you may think it as a unitary evolution and reduce and after the system undergoes unitary evolution, you reduce your description. You're just interested in reduced matrix, right? So this is a parallel between the measurements and the evolution. We have already discussed it. So actually, maybe the things that illustrate further this, just let me tell a couple of quotes on the so-called classical quantum states and let's consider the state which looks like, let's say, you've got some classical random value, and these are the probabilities described in the classical random value x. And I've got the things such as this is just orthonormal states. So I've got things like x. Such state can be regarded as a register that stores the results of measurements. In that case, this just stores the information about the value of the classical random variable, right? And let's say it's size. For example, our system, of course, it can generalize a bit. It can, for example, assign this not projected, not the density matrix. So anyway, or another version, arbitrary density matrix. So we get two systems. One of them serves as a system where we store the values of our random variable, and the other represents the state of our system. That's typically okay. So this is an example of so-called classical quantum state. Why it is classical? Quantum state. And for example, it may be the state which can be obtained as a post-measurement state, and I perform some measurement on the first subsystem, and this is the result. And I don't know the result. So Px just probabilities that the result of my measurement is x. So it's described by the.
And X is a classical register.
Yes. So just serves as a label, so it may be whatever. If you want, it can be eigenvalue of observable, maybe the label that labels the outcomes of your experiment. Okay, an interesting thing about this, so it says raw CQ, classical. What happens to this state when I perform measurements on the first subsystem using if I perform measurements x, so the projectors, it implies that I'm using the projector, the x. So the measure, I just measure first apply the measurements to the first part of our system. An interesting thing is that measurement will not change this state. So if this initial state looks like this, then the post-measurement state will be the same. Yes. So it keeps CQ intact. What does it mean? That I perform measurement and I don't know the result. So it means that I would say Tx raw CQ Tx. Example when the measurement do not disturb the state. So this is a special kind of state which remains invariant under the measurements, under certain measurements. So.
But if we measure the second part, the state will be changed.
Yes.
Of course.
And actually, if you will use the measurement in different bases, so and the same will happen to the first part. So actually, certain measurement and certain kind of state. But it explains why this measurement, this state is called classical. So this is a characteristic of classical system, which is not changed under the measurement. So this non-disturbance channel that mimics similar representation. Okay. The so-called classical quantum channel. Okay, once again, we've got the input quantum state described as a density matrix, right? And we will have the measurements in bases, for example, T. Okay, you have to know the measurement bases. Okay, post measurement state rho E. If I'm just trying to describe the result of the measurements, conditional will be things like K, Okay, let's generalize a bit. What actually it will modify the channel so that I will get things like, I would say, EB. If after that I will discard the system on which I have performed measurement, I will get things like this. So actually, once again, this is a projector defined on the face of our system A. We are system of our initial system, and actually this is the state that describes the other system B. Right? Actually, physically it can be the same system, but it just, if I do this, I will get the result. Okay. So I have got the map. When we have the input state described by the density matrix rho A, and the output state is described by the matrix rho B. So we've got this state B, classical quantum. Okay. the channel somehow mimics the preparation procedure. Yeah, yeah. So I perform measurements, look at the result, and depending on the result, do something. Prepare, for example, my quantum state. And this, as compared to the statistical ensemble, so instead of using generator of random numbers, I'm just using measurements. That's the only difference here. So, what's interesting thing about this classical quantum channel is that this is so-called entanglement breaking channel. What does it mean? It means that for example, we say that the quantum channel is the entanglement breaking channel. If for any entangled system, for any entangled state, let's say psi, say AC, I need to introduce not to confuse the it is a receiver of the target space of our entanglement of our channel. So the entanglement channel applies only to the A part of our entangled state, right? So apply. This is a pure state, so it's described by the projector. So the result is separable state. So any entangled state is mapped into a separable state. So entanglement appears to be broken. So the channel, from this interpretation of the channel, that the preparation procedure actually will break the is separable. Okay, so the question is to demonstrate. For example, we can consider the entangled state as a maximal entangled state, right? So, for example, let's suppose that we have AC as entangled one. Oh, if you want, EP, EC. will happen if I apply classical quantum channel to this state? Yes, I will get things like, once again, it will be about, this is maybe it's going to be tough. So actually, to simplify the notation, I can, for example, use the same basis, so that they had I and K from the same basis, so they just mutually orthogonal. It is not necessary, but it will simplify the result, so we will get things like
Alexey Vinslavic, I guess there also should be projector on K state.
no.
If we use our definition of classical quantum state, we have obtained there matrix
definition
element.
was that the K state is reduced. So we have traced out the system A when we were introducing the classical channel state.
Okay.
So actually, I will get things like this. Right. See, right. Okay, so this is something which is proportional to the pure quantum state. So it is an unnormalized, certainly it's an unnormalized state. For example, if I use this assumption that A, J, and K are mutually orthogonal, I will get boxes like it depends on K. But this is unnormalized state. So you've got things here like okay, and actually unnormalized indicators with tiles, so tiles implies that this state is unnormalized. So normalization will give me such things like pk. So we have already encountered such kind of results when we were discussing the remote preparation of quantum states.
Right.
So yeah, perform the measurement only on one part of my state. So this is the initial state, and then I perform the measurement in brackets K on the state on the system A. So this is what will happen after that. So the state is collapsed onto the state on the other side. And for the C system, we will have the state. So that's it. So we've got this statistical mixture, and the mixture for this tensor product, this is one of the density matrices, and this is other for the density matrix. And this is separable state. So entanglement appears to be broken, and an important thing that we applied our channel only to one part of our entangled state. Okay. Actually, entanglement breaking channels are important class of quantum channels. Preparation procedure that we have described introducing the classical quantum channel is just one of the examples. Entanglement breaking channel. Okay. Let's may appear there is comes from the unitary evolution, right? Let's now I want to go in the reverse direction. We've got quantum channel, and I want to describe it in terms of isometry. So we will be talking about isometric extensions. Extension. Of quantum channels. Okay, we're already familiar with the operation which is known as a purification. So we've got this statistical ensemble, we've got the density matrix describing the statistical ensemble, and we can purify the system. You may enlarge the system in such a way that the density matrix for A I represent this matrix with the help of pure state in enlarged space in such a way that this P actually is nothing but sometimes a system which you use to extend the system, enlarge the system, is called a reference system. So maybe I will change the notations a bit. So we can say that instead of B, I will introduce R, capital. Now this is a so-called reference system. And this is a purification of the density matrix.
And trace R also. Yeah?
Yes, yes, of course. Please. Once again, isometric. Extension. So the idea is to represent the density matrix with a few states. So it's a bit backward direction. Actually, initially we was starting from the pure states, and after that, for example, we described the situation when we don't know exactly what the pure state we have. So, and we describe this in terms of the density matrix, but now it's vice versa. You've got density matrix and we want to introduce this pure state. An interesting thing about maybe for example, if I know this density matrix, just an operator, how can I construct this reference system? An idea can be, for example, let's suppose we have this anomalized state. Things like, looks like so this orthonormal basis in HA and HR so what I want to do is to apply the operator and I want it. So this is anomalized operator. So actually, I'm assuming that the dimension of the reference system either coincides with the dimension of our system A or it's larger. So it should contain enough of cats to construct this maximal internal state. So this is just generalization of the above state. 5 plus. So this construction, just what I want to do is just to apply this operator. The result will be this. I will just will be things like this. Actually, this is explicit expression for the state y. So the exercise is to show that this, so actually can show that this is trace out you give me so this is a universal construction of a purified state. And this purified state is obtained using the maximally internal states. So in terms of the maximally internal state, I can obtain one of the purifying state. All the other purifying states are obtained under the action of the unitary operator acting on the R part, on the reference part of our system. It depends on the choice of the methods. So this is everything that will be changed. So so this is the exercise. So this way a bit more general as compared to the, if you know the representation of our operator as the statistical ensemble of quantum states, right? So it doesn't require the knowledge of such kind of representation. It just requires that you know the operator itself. That's it. So now I want to introduce similar notion for quantum channel. So quantum channel, so purification the so-called isometric extension. Of quantum channel let's suppose it's something like it be looks like is described in terms of it looks like we have rock age. So we've got isometry. Just let me change the notation. This is isometry from A to BE. Isometry that acts on the substance. This can be, actually it can be unitary operator because we've got different dimensions on the spaces. So the unitary actually implies that we've got the, we have the dimensions of these Hilbert spaces equal. And it can be, and as a result, it can be inverted, right? But for the isometry, this is not the case. So we've got things like E to BE. So it looks like unitary evolution. Right. So I extend the system and introduce the analog of unitary operator. And so now I have to trace out environment. So purification actually implies a description in terms of unit of isometric operator. So, okay. So our extension actually is described by this isometry. So I have to introduce isometry in order to describe extension. And actually it is a useful way to introduce quantum channels. That's why it is important. Okay. For example, can we see something? So examples. For example, let's suppose we have the channel, for example, bit flip channel. It looks like we've got So what I want to do, I want to introduce isometry. So isometry is something which is formulated in terms of few states. So for example, I have to introduce things like this. This is psi. And let's see where it is. And here. Let's have this V. So this is nothing but the result line on the side. So this is a quantum state in our initial, in the space of our initial system. So it plays the role of the system A. And actually this is a quantum state in the space of the system B. And it silently assumes that these spaces are the same. So the states on the L's and both sides isometric. That's why I'm not changing the notations. This is the case. So maybe it's useful to introduce. Let's suppose so we assuming that the state qubit state, our qubit state, right? So extended version on the right hand side assume that we have two qubit space, right? So we have here dimensions equals 2, and the dimension for the space on the right hand side is 4. So actually, if I want to show it in the matrix notations, V V. So the first column is nothing but the ket vector obtained by acting the isometry on the our first basis vector, right? So we have here, so we have to replace here psi with 0, right? So we have got here 0, 0, and here 1, 0, 1. So it looks like this, I'm sorry, no, because we've got here 0 and sigma 1. X on 0.
Will be 1.
So this will be 0 and this will be 1. Once again, what I want to do is to compute the coordinates of the first column. So of this, the coordinate representing this vector. So 0, 0, this is the first coordinate, and we'll get things like So all other coordinates are 0 except in our notation this is the last coordinate 1 1 and we've got P like P. That's good. So the space is 4-dimensional, that's why we have 4 coordinates here. Right? And the next column will represent the coordinates for the next image. So now we will change it a bit. This is 1, and actually this is will be 0. So we have things like 0, here P, so clearly we have 2 states, and these 2 states are mutually orthogonal, and the length of each of these 2 states equals unity. Right. So we have 2 mutually orthogonal and unit quantum states that mapped onto 2 mutually orthogonal quantum states, so normalized quantum states we've got. So that's it looks like similar things appeared for the unitary, but for unitary I will have to unitary represented by the square matrices. So I have to two additional columns, and the only thing to do this is to extend the dimension of our initial system. If I manage somehow to extend this, no problem. I can actually transform the isometry into unitary. But the price to pay is that the initial space should be extended so as to have the same dimensions on the both sides of our question. So actually, yes, it is unitary, and you can check this, for example. And the result will be so you may multiply these two matrices, right? So actually the result will be nothing but identity matrix 2 by 2. All right. Okay. Another interesting thing, what about what will happen when I change? What I think? By 4 matrix. Unfortunately, it can be unit. It can be a unit. Actually, you'll get the projector. Things like. Is it right to have something like this? Just compute this result. So, an interesting thing and this is the isometric. And you may check that what will happen each side. Write the projector for this state and trace out the reference system. Or if you want an error, I may talk about the environment. And you have things like so that's all we need to introduce a channel. Of course, the channel is linear, so if this is the case for projectors, so this will be the case for the density matrices, because any density matrices is just a linear combination of projectors. So, so that's more than enough. Okay. So actually, what we have for example, this example introduces a general idea. If you have, for example, the Krauss representation, so looking at the Krauss representation, I may define the isometry, and this isometry is nothing but will be the surface describe the isometric extension. So sometimes such kind of isometric extension is called as time spring dilation. So isometric extension time spring. This is the name dilation. This is a popular way to describe, for example, Gaussian channels. Okay, dilation, extension dilation, and things means the meaning is the same. So, what's the idea? For example, if I have once again Krauss representation. So the corresponding isometry can be described. So, for example, I have this HA. This is the space. Let me be more explicit about the system. So HA, I want to translate into R, and I want to describe the heavy notations. And the idea you get psi each. The quantum state for our system is mapped into E psi. Of course, I can change the letter to B. It complicates notation. So, but the result will be what do I do? I can construct it. Sorry. So once again, this is the orthonormal basis in the reference system, for the reference system. So it's sometimes. And now we can show that actually it's not very. That is. In what follows, I will reduce notations and I'll get these things like just B. Because it's clear. It's meant to be. So we will have can be easily checked. The trace of a power. It can be done, of course, using straightforward computations. Right? So actually, so just check it. So we have to multiply this get vector and by the vector on the right side and trace out. The reference system, assuming that this is mutually orthogonal states. So you know how to say result. So what about this? Actually, yes, I've got this mapping. So what I have, what who says that this is isometry? How to check that this is isometry? So actually, it is not very. Introduce notations for our geometry. Actually, this is nothing but the so if this is the case, then this is so I've got this bra. it's good things to introduce two different indices here because I have to multiply. So
And these are also orthonormal ones. I, R, and J are
yes.
orthonormal.
So, I'm using orthonormal bases, except for the cases where it was specially mentioned that it's not orthonormal. So by default, the basis is orthonormal. And yes, so we will get things like this, and actually I will get this one, G, I, and here I will get the scalar product. The scalar product. And now, this is nothing but the Kronecker symbol. So we will get things like, but the cross operator means completeness condition. So this sum is nothing but the identity operator. And of course, the other thing which I have to show is that this is a projector. And actually I have to check that this operator squared is nothing but the initial operator. But I won't check it here. It's a bit long isn't it? So we will interchange this operator, and you will have this the unit rank operator instead of the scalar product. So actually, squared will have two sums. Many indices, but after that I have to use the orthogonality condition and we'll simplify the expression. So that's why I will get the same thing. It can be checked, but I won't do it here. Okay, just check. So this is the idea of describing describing the quantum channels in terms of isometries. So I've already mentioned that this isometry is, let's see, so I want the last remark, in fact the isometry can be turned into the unitary. But the idea is that we have, for example, here, right? So now, let's see. So here I introduce reference system as well on the left side. But actually I have my isometry is only to these vectors, right? So if this is Things such as basis vectors, with basis vector in my system. So this mapping defines the result of these vectors, right? But what about the other vectors? It's not clear. So this should be arbitrarily defined, but this vector should be orthogonal to the vectors, defined vectors. So they J, this is orthogonal to and they should also be mutually orthogonal. So it looks like if we get back to our example for the big channel, we've got things like, for example, I'm not sure. See, this is 1P. 0, and here you've got 2. So I have to choose other columns. For example, it's easy to do. I might say that we have 2 vectors, and for example, the other vector can be P. I interchange coordinates and change the sign of one of them, and similar thing will apply to, for example, so this is what happens when I use and things like this. For example, it's just an example how I can introduce unitary. Of course, there's the arbitrary because I can choose, there are many ways to choose these remaining 2 vectors. So this is just one of them. So, any suitable combination of this vector will do it. It's useful to think about isometry in terms of unitary apparatus, but sometimes it doesn't give us any considerable advantages. Okay. So it's all about quantum channels. It's a very short introduction, actually. But once again, The last thing to mention is the complementary. Quantum channel. Uses the unitary extension. So let's suppose we have quantum channel, right? So we have, say, quantum channel. Also, we have let's see, isometric extension. And similarly, I have introduced unitary, and I have enlarged this state, my initial state. So it looks like I have defined somehow unitary. So I've got RR2. And now everything is described in terms of unitary. So the idea is that this unitary extension, because there is some arbitrariness in defining the unitary. For example, of course, I know the isometry. Isometry is more or less fixed, for example, by Krauss representation, right? But the unitary is not so is not unique. But nevertheless, the idea is that this is the expression where the unitary, where the operator, where reference system and our system enters symmetrically. So this is the so-called symmetric representation that we have. Our system and reference system on equal footing. So actually, what I want to know. Okay, so the question, of course, it can be extended to not only to such states, but to any states, right? So the idea is that this unitary can be used to define the so-called okay. So I've just reduced the notation so that the unitary acts in the same space, so in the standard space. So the idea is that I can reduce trace out the system E. That describes the state of inventory. Let's say this. Once again, I'll be using similar notations. Of the reference system. So complementary channel describes what happened so it's a useful measure if you want to, for example, estimate information leaked into environment. So we've got our system, we've got environment, we've got this interaction is described in terms of quantum channel for the reduced matrices, but this interaction may be modeled using the unitary, and tracing out of our system will give us an estimate for the state of environment. So this density metric can be used to estimate the information that flows into environment. And actually, there is arbitrariness, but it can be shown that sometimes the measures of this information are invariant with respect how I extend isometry into the unitary. So of course, we have the result for the environment. Okay, so I'm not sure that. So,
Alexey Denislavovich, shall we take a break now?
yes. So now I want to finish our discussion of quantum channels, and we'll move on to the distance measures and field realities.
And the information that is estimated by with the help of complementary channel is bounded by Kolevo bound.
Yes, if you know the density metrics, so you may use things like entropy to estimate the uncertainty and to estimate the flow of information. But this topic we won't discuss any detail. Actually, it is one of the ideas in information analysis when you have your system and the space of your system is enlarged, and this reference plus your system are undergoes a unitary transformation. So, and for example, you can use this things such as purification. So you've got some density metric, you will purify them, and after that you will introduce this isometric extension described in the channels, and these channels and this isometry is used to estimate all needed different density matrices. And for example, but of course, detailed discussion of these procedures may be for advanced courses.
Okay. And we also have like a question about one of the tasks.
Yeah.
So when we have here like two observables like sigma 1, sigma 3,
Yep.
then we know that commutator will be 0 because commutator E sigma 2.
Yep.
2E sigma 2. Yeah, so what we need to do here, because like this thing is just because of this, we need,
I mean, you should choose the quantum state that nullifies the right-hand side. So, in your case, the condition is, sigma 2, yeah? So you have things like 2, yeah? So we want this to be 0. So what are the quantum states that gives you 0?
Okay.
okay, I think.
Мы так и делаем сейчас.
Ну,
Там коммутатор у нас был посередине. Да?
не, коммутатор-то все нормально, типа, абсолютно все в порядке.
Нет, это понятно, я просто...